Welcome back. So in this next lesson, we're going to pick up exactly where we left off in the previous video. The only thing I've done differently here is I've already remixed the sketch we were working with into a different one, so I don't accidentally override it. And I've made a couple of small changes. I've in the way that I'm centering these graphs here. That's a tiny little detail. So if you haven't watched the previous lesson yet, please go back and do so. Where we ended up with is with these graph objects that are essentially taking a stream of numbers coming in, right? Recording, in this case, the 60 most recent values, and then representing them in some sort of visual way. So here we have a simple graphical representation as lines, but you could imagine this history of values could be represented in any kind of way that you could think of. And we spent a little bit of time first developing the graph and then spending some time creating a class for the graph so that we could run multiple instances of this concept of a graph so that we could record different number streams using the same ideas. So here right now I'm recording the mouse cursor moving from left to right and the mouse cursor y coordinate moving from up and down on the screen, okay, as two different graphs. However, we pointed out at the end of the previous video that there's a bit of a problem in the way our graph class is written right now. And the issue has to do with this line over here. So when we try to take the value we've recorded coming in, so this could be mouse X, this could be mouse Y, again, this could be any stream of numbers. Imagine maybe a sensor, or maybe you're turning a potentiometer with a knob to record some kind of value. You get numbers from that, you want to record them as a history. The one important piece of information we need to have about the values we're trying to represent is the minimum and maximum. And by that we mean what's the smallest value in our data and what is the biggest value in our data. And the reason this is important is that without this, it's very difficult for us to come up with different mappings for the data. And now, just in the interest of moving forward at the end of the last example, we're making a big assumption here with the data, which says whatever the values contained inside the array, when we try to map them, right, we say they go from 0 to width. And it kind of works here with the mouse y coordinate because my screen area is square-ish. Okay, so that's really a fluke, but this is really incorrect here, right? So the fact that we don't really know what these values are going to be because we've abstracted that idea outside of our class, right? We said we're just going to add values to an array, and those values could be mouse X, they could be mouse Y, they could be anything, any kind of other number stream our program could get its hands on. So we cannot have this assumption here that values will go from 0 to width because that simply may not be true. Okay? So how do we know what the boundaries of a data set are? Well, it depends, right? Sometimes we know, like in the case of mouse X and mouse Y, we could imagine, we could say, okay, well, if we need to know the boundaries, let's create a minimum value, right? And a maximum value as attributes of our graph. But how are we going to determine what these values are? So if when we were working with the mouse cursor, that's very easy. Those values just go from 0 to width, 0 to height, so we already know what they are. But what if we're dealing with real-time data coming in? Again, going back to my sensor example, what those values are might change every time the program runs a little bit. So a useful thing we can do with a real-time data stream like this is calculate those minimum and maximum values as the program runs. So we don't have to predetermine what the minimum and maximum is. We can just let the numbers tell us what the boundaries are as we see more and more data coming in. So we're going to do this as an exercise for the mouse X, mouse Y here. Even though we already know the boundaries for this data set, we're going to instead write the code that's going to calculate this minimum and maximum for us, kind of dynamically adjusting to the range of values our program has seen so far. And that's going to come in handy down the road when we start to look at other data sets that are not just so predictable or so easily understood as mouse X and mouse Y. So even though we do know what the min max are for those particular values, we're just going to treat them as an example here and use it as an excuse to write a little algorithm that's going to find out what the min max are inside this array values. Now, there's a couple ways we could approach this. We could look at, what are the minimum and maximum values inside the array at any given time. But that's going to create a lot of, because it doesn't take long for 100 or 60 values to get filled up. Right? If I am going to just comment this out here for a second. We don't necessarily want our drawing to just kind of scale up and down all the time, to only show us, kind of zoom in and out constantly, to only show us the minimum and maximum of the 60 values that are currently being displayed. Instead, the way we're going to approach this is we're going to say, what is the smallest value we've seen so far, right? And what is the biggest value we've seen so far since the program has started? And those are going to be the ones we use to set the boundaries of our data. So the trick I like to use to do this is in the constructor, we're going to set our minimum at an arbitrarily large number. And by that, I mean, I'm literally just going to lean on the number 9 here for a little while. And now I got a whole bunch of 9s. And I'm just making here, I do make an assumption that I'm not going to see numbers bigger than this coming in as a data stream for my graph class. Okay? I think it's a safe assumption. And we're going to do the opposite for the maximum. We're going to make this an arbitrarily small number by putting a negative sign in front of it. So now I have an arbitrarily huge number as my minimum and an arbitrarily small number as my maximum. Okay? And the reason that's going to become important we'll get into in a second. Okay? So these two values are going to define the boundaries of our data. So how do we calculate the minimum and maximum? Well, it's quite simple. We're going to say every time we add a new value to the array, right? So we're going to go inside our add function because we know this code runs every time a new value gets added. We're going to take a look at this new value after we've added it to the end, and we're going to compare it with the current minimum. Okay. So we'll say if this new value is smaller than our current minimum, okay, then we've found the minimum for our data set so far. We'll say this dot min equals new value. Okay? We have a new winner. And we'll do the same with the maximum. We'll say if this new value is greater than our maximum, the maximum is now equal to the new value. So this little comparison here is going to basically update min and max with the new value whenever we find a value that is smaller than min or greater than max. And that's why at the beginning here we picked arbitrarily large and small numbers. Okay? It's very easy to find a value that's smaller than this number, whatever that is. Essentially, the first value I add to the array is guaranteed almost to be smaller than this number. So that's going to become my new minimum. And as more numbers get added, more values come in, I'm going to have to find one that's even smaller than that to become the reigning champ of the minimum values. And the same logic will apply to the other end, to the maximum. Right? This is a really, really small, small negative number. So whatever value I add to this graph is bound to be greater than this number. That's going to become my maximum right at the beginning. And then as I add new values, this number won't change until I find a bigger one. Okay. And now that we have this information, we can do this better here. We can fix this problem. So when we're going to map the content of our array over here, we're no longer going to make the assumption this goes between 0 and width. Instead, we're going to make an educated mapping here. This goes between this dot min and this dot max. Okay. So this is the smallest value in our data set. This is the biggest value in our data set. And map is going to use that information to decide what to do with the value we're putting into the map function. The output here is not affected. It's still going to try to map it from 0 to the bottom here. But now what this is going to do is this is going to essentially, you can see like as I'm moving more to the right, it's kind of scaling the whole graph, right? This is now adjusting to the range of values it has seen so far. Okay? Let me refresh this so it becomes a bit more apparent. So if I only move my cursor in this area over here, right, this is now the biggest value it's seeing. It is up here, and the smallest value it's seeing is down there. Same thing with the up and down. But if I move my cursor all over the window, right now, all of a sudden we have a slightly bigger universe. Okay? And now those, the smallest value has become 0 and the biggest value has become width and height. So now it's adapting to the full range of values. So this is very useful, especially when you're working with real-time data, because you don't necessarily know ahead of time what range of values. Let's say you create an object that has some sensors embedded inside of it, maybe a light sensor, right? And then when you turn it on, you want to do something based on the amount of light being received. So your program can adapt to what is the smallest amount of light and what is the biggest amount of light seen so far, and then map things within that range without necessarily having to hard code those numbers ahead of time, because other variables might in fact impact this sensor reading, for example, that are not under your control. So this is handy. This is also a useful thing to do down the road when we work with predefined data set where they're not real time. Maybe they're archival data sets, spreadsheets, things like this, where we'll be able to scan through the data and quickly determine what are the boundaries, what is the maximum and what's the minimum. So we can use a similar algorithm for doing the same thing. Okay? So this works both for pre-recorded data and real-time data. And this part is a little awkward, I'll admit, just putting in these huge numbers. But again, if you don't expect to see numbers that are bigger than this or smaller than this, then this trick is going to work just fine. Right. So finding the min and max of a data set is really important because it allows us to do mappings correctly. And now in this case, I can remove this comment because we have fixed the problem. We can now perfectly handle any type of data coming in, right? And the graph is going to scale itself, adjust itself to its new minimum and maximum as new values are added, right? So the map is going to interpret this differently based on what's the smallest value, what's the biggest value across both of these axes. So the other idea we're going to explore in this lesson is we're going to talk about get into some basic data manipulation. And one of the simplest things, but also useful things we can do, especially with real-time data streams, is talking about smoothing or averaging the data. So here, for example, I could simulate, a very noisy or hectic data set by moving my cursor very quickly. Okay, so we're going to talk about how we would, kind of smooth this out, right? Just make it a little bit less jumpy and less susceptible to change. And we're going to do this using averaging. So averaging, as I'm sure you'll know if you remember math from school, is taking the sum of a number of values that we have and then dividing by the number of values. Okay? So if you have 10 numbers and you want to take the average, you add them all up, you divide by 10. Now, in this case, averaging all 60 of our values might be a little bit too much. Okay, if we just average all 60 values, this might be a little bit too much. So we're going to instead create a separate idea where we're going to average maybe only the last 20 values we've recorded. Okay, not necessarily the whole set, but just 20. And the size of our average is going to effectively determine how much smoothing gets applied to our data stream. So rather than try to average the entire graph, right, all of the values over here, we're only going to average a smaller subset of the values, let's say the last 10 or the last 20. So essentially we're going to be calculating not an average of everything we've seen so far, more like a rolling average. And we'll have the size of that average not necessarily be tied to the size of our graph. Okay. So in order to do this, we're gonna create a separate class. Okay, and this class is going to have a different job than the graph. So the graph is going to be recording a history of numbers. Okay? It's going to be similar to the graph in the sense that it's going to record numbers, but instead of recording a history for graphing purposes, it's going to record a shorter history for averaging purposes. So it's going to have similar ideas in it. And let's call this class an average. So we'll need a constructor. Okay? And let's put a parameter in the constructor. We're going to call this parameter n. And that's going to be the number of values we're going to be averaging. Okay? So, okay. And then we'll need an array. Let's call it values. And this array is going to contain the history, much like we do with the graph here. The only difference is what we're going to do with this history. So in a way, like values here and max values, kind of the same thing as values in n. Okay, so I'm just using n here for short instead of max values. So n will be the number of samples to average. Okay. So that's going to be our average class. Okay? And what we're going to do to demonstrate this is instead of plotting mouse x and mouse y, we are going to plot in the graph 2 here. I'd like to get to a point where I can average the value of mouse x and then plot that instead. So we're going to have mouse x on the left, and then we'll have our average mouse x on the right, so we can see the difference between the two. So let's create an average object before we work more on our class. So we'll create a new average, and we'll put in 20 values for the average. So our graph has 60 values, but we're only going to average the last 20. Okay? And the bigger that number, the slower the rate of change will be. We can play with that once we've created the code for averaging. Okay, so let's go back down here. And again, you'll notice I like to use those dividing lines here to separate out different elements of my sketch. Okay. So we said the average, we have a constructor, and we're going to store two values inside of our average object. We'll have the number n, which is the size of the average, and the values themselves that we're going to record. Then I'm going to write, much like I did with the graph here, I'm going to write another function called add. And just so we don't confuse them, maybe let's call this one process. I don't know, just making up these names. We'll call this new value. Okay? And the job of that function will be to add a new value to the running average and return the current average value. Okay? So the way this is going to work is we're going to say we want to be able to add new values coming in to this average. We're going to save them inside the values array. And then once we've added a new value, we're going to immediately calculate and return the average of everything we've seen so far. Okay? So let's implement this. And you'll see it's pretty straightforward. In many ways, it's very close to what we've done with the graph. Okay? So as we get new values, right, we'll say, let's push this new value at the end of our values array. So I'm using the same name here of arrays, but just be very clear on this. These are completely different variables, right? This values array is part of the graph class, and that values array is part of the average class. So I'm using the same language, but they are completely different and unrelated arrays. But we'll use the same idea here as we did with the graph, which is to say when values.length is greater than the number of values we want to record, we know it's time to remove the old ones. Okay, so same idea as with the graph. So this records a history of the last n values, or in the case of this instance, 20 values. The different thing is what we're going to do with this average. So instead of drawing it the way we're doing with the graph, we're going to do a little bit of basic calculations. So we said before, how do we calculate an average? Well, it's very easy, right? We're going to say, we're going to take all the values we've collected so far. So let's go through them using a for loop. And we're going to add them up together. So we'll say sum plus equals this dot values bracket I. So we're going to go through the array, right, one at a time, just add all of the values onto this sum variable. And then once we've done this, the average, I'm just going to use this for short, is going to be the sum divided by this dot values dot len. So however many values we have inside the array, we're going to divide the sum by this. And then we'll return this value as well at the end. So this is kind of a new thing we haven't recapped yet so far this semester. So when we use the keyword return, that allows a function to not only take some values as input, as parameters, but they can also spit out some new value. Okay? So now we can say, okay, we're going to add a value to our average, and what we're going to get back in return is going to be the average, right, of all the values we've collected so far. So let's test that into our program. So now that we've created an average object over here, we could say, okay, this graph here is going to show mouse X. Then we're going to say average.process mouse X. So this is going to call the code inside the process function down here. Okay. It's going to say take new value, so that's going to be a mouse X here coming in, add it to the array, then calculate the average so far, and then return the calculated average, which means this line of code here, this thing here, actually this outputs, right? This actually outputs a value. Okay? We could store it into a variable, okay? And then we could use that to add to graph 2. So now it looks like they're the same, but you can see that graph 2 is actually a lot smoother. So if I'm moving slowly, they're more or less the same, right? The averaging doesn't have much of an effect, but if I'm changing my mouse quickly, right, you can see there's like peaks and valleys on the left. This is the raw direct value that I'm recording inside the history. On the right, this is the average value, the last 20 values. So it still gets those bumps, but they are much smoother. And of course, a nice thing we could do here with the syntax of the language, we could say, because this is outputting a value, right? This is outputting a value, putting it into this variable average. We could do away with this variable altogether, and we could simply say something like this. Oops, I meant to cut here. We could simply do that, and then we could get rid of this variable altogether. So now we have two graphs. The first one we're adding mouse X, and in the second one we're adding mouse X, but then processed or filtered through this average object that we created. So now we can have kind of these two concurrent values, right? They're coming from the same data source, but one of them is raw or just real time, and the other one is being average or smoothed out. All right, so we're going to leave it at that for this video. And as an exercise, I would encourage you to think about, now that we can record a history of some values, we can also have different versions of that history. We can have the raw one, the average one. What kind of visual representation would you imagine for this history of numbers, right? And you could stick to mouse X as your input because that's an easy way to get some numbers. what kind of different visual representation can you think of that isn't a series of lines? Admittedly, that's probably like the most boring way we could represent this data. It does have the advantage that we can see it change over time very nicely in this format. But could you come up with another way essentially of drawing, right? Another way of interpreting this draw function here inside the graph as a way to practice, ideas of mapping values, kind of taking values from the history, numbers, translating them to different positions on the screen, maybe different visual elements, or maybe if you want to really challenge yourself, think of a visual representation where you could juxtapose the raw version right next to the smoothed version and have the two have some kind of interesting interplay with each other. So that can be your code exercise for this week. Sort of create a version of this program where you provide a different visual interpretation that isn't a series of lines. Okay? All right, so I hope you enjoyed, and I'll see you in the next video.